I am Buğra Çaşkurlu from the Computer Engineering Department of Top University of Economics and Technology. Today, I will present new results on test cost minimization in database migration. This is a joint work with my student Utku and colleagues Mani and Piotr from the West Virginia University. Now, an important ubiquitous task in modern cloud systems is the migration of databases from one location to another. In practical settings, the databases are migrated in several shifts in order to meet the quality of service requirements of the end users. Once a batch of databases are migrated in a shift, the applications that uses the databases on that shift are to be immediately tested. Testing an application is a costly procedure, and the number of times an application is to be tested throughout the migration process varies greatly depending on the migration schedule. Now, in this example, databases B1 and B4 are migrated in the first shift. Immediately after that, applications A1, A3, and A4 are tested since they use B1 or B4. Databases B2 and B3 are migrated in the second shift, and applications A2 and A4 are tested afterwards. Notice that A4 is tested twice throughout the migration schedule. Now, database migration is often necessary due to several reasons, such as database software or hardware updates, merging of two companies, or other cost-reducing business factors. Typical concerns for the database migration are its cost, potential security breaches during migration, and the quality of service requirements. We now formally define the capacity-constrained database migration problem. So in that problem, we have a set of M applications. The cost of testing an application AI is denoted by CI. We have a set of N databases, and the size of database BJ is denoted by WJ. Application database dependency relation can be captured by a binary matrix D, where Dij is equal to 1 if application AI uses database BJ, and Dij is equal to 0 otherwise. Vector L of size K, which is part of the input, keeps the cumulative size of the databases that can migrate in each shift. We use Xi to denote the number of times application AI is to be tested throughout the migration process. Now, we consider 8 variations of the CCDM problem that restrict the input space in 3 different ways. We have 2 models concerning application testing costs. In one of them, all application testing costs are the same, and in the other, applications can have arbitrary testing costs. Similarly, we have 2 models for database size. In one of them, all database sizes are the same, and in the other, databases can have arbitrary sizes. We also have 2 models for shift sizes. In one of them, all shift sizes are uniform, and in the other, shift sizes are arbitrary. A model of the CCDM problem is a triple specifying the values for the parameters. For instance, the notation argconst unif refers to the CCDM problem in which application testing costs are arbitrary, database sizes are constant, and shift sizes are uniform. We use a star to denote both values for a parameter. For instance, the notation star arg unif refers to the 2 models in which database sizes are arbitrary and shift sizes are uniform. Similarly, the notation star star non-unif refers to all 4 models in which shift sizes are non-uniform. We now define the CCDM problem and its 2 special cases for which we present results. Now, in the capacity-constrained database migration problem, the input is the portable CWDL, and the goal is to partition the databases into the shifts such that the total application testing cost is minimized while respecting the shift size constraints. The CCDM2 problem is a special case of the CCDM problem in which all application testing costs, database sizes, and shift sizes are uniform. There are only 2 shifts, and each application calls at most 2 databases. The CCDM3 problem is a special case of the CCDM problem in which database sizes and shift sizes are uniform, and each application calls at most 2 databases. Now, we present a CCDM example. In this CCDM example, we have 4 applications. Their testing costs are 1, 3, 5, and 7. We also have 5 databases whose sizes are given as 1, 1, 2, 1, and 3. The application database dependencies are as depicted with the lines. we have 3 shifts with sizes 4, 3, and 2. Now consider the assignment where database B1 and B2 are placed to the 3rd shift, B3 and B4 are placed to the 2nd shift, and B5 is placed to the 1st. Notice that A1 is to be tested 3 times, A2 is to be tested twice, A3 needs to be tested twice, and A4 needs to be tested only once, with a total application testing cost of 26. Now we will give the results from the literature. It is known that all 8 models of the CCDM problem are NP-hard. All 8 models are fixed parameter interactable under P not equals NP, where the parameter is the number of shifts or the maximum number of databases that's called by an application. All 4 models of the CCDM problem captured by the notation star R star are fixed parameter interactable under P not equals NP, where the parameter is the number of applications. All 4 models of the CCDM problem captured by the notation star star non-unif are fixed parameter interactable under P not equals NP, where the parameter is the maximum number of applications that calls a database. There is also a randomized 3/2 plus epsilon approximation algorithm for the CCDM2 problem. Now, I will talk about our contributions. We show that there is no 2 to the small o of n time algorithm for the CCDM2 problem, and hence for the CCDM problem, unless the exponential time hypothesis fails. So basically, any algorithm that solves the CCDM problem should have an exponential time. We give a 2k minus 1 over k plus epsilon approximation algorithm for the CCDM3 problem. We show that APX hardness of some models of the CCDM problem implies APX hardness for the weighted minimum bisection problem. We adapted some heuristics for the hypergraph partitioning problem for the CCDM problem and compared their performances. Okay, let's continue with our theoretical results. Our theorem establishing a lower bound for the running time of any exact algorithm for the CCDM2 problem is as follows. Unless the ETH fails, the CCDM2 problem cannot be solved in time 2 to the power small o of n. So the proof is a bit complicated, so I will give just a sketch of it here. Let pi prime be a 3CNF formula with m star clauses and n star variables. From pi star, we construct the 3CNF formula phi with O of m star variables and O of m star clauses, such that phi is not all equal satisfiable if and only if phi prime is satisfiable. From phi, we show that we can construct the CCDM2 instance I with O of m star databases. We prove that phi is not all equal satisfiable if and only if the databases in I can be migrated with cost at most this much. This implies if an algorithm can solve the CCDM problem in sub-exponential time, then 3 SAT could be solved in 2 to the small o of m star time, but this violates the ETH due to the specification lemma. Now for the CCDM3 problem, we show that there is a randomized 2k minus 1 over k plus epsilon approximation algorithm. The algorithm fills the shifts starting from with the first one until all databases are assigned to a shift. When filling the shifts sufficiently many databases are selected uniformly at random from the set of unassigned databases. Now in this figure, we have 6 applications with testing costs 1, 2, 1, 2, 1, and 2. We have 6 databases with unit size, and the capacity of each shift is 2. The algorithm randomly assigns 2 databases to the first shift. The 2 of the remaining 4 databases are selected at random and assigned to the second shift. The remaining databases are placed to the third shift. Since there are 3 shifts, the algorithm ensures to obtain a solution that is within 5 over 3 plus epsilon on expectation. In this example, in the optimal solution, databases are placed to the shifts in their index order with a total cost of 9. However, the solution found by the algorithm has a total cost of 15. Now I will move on to the inapproximability result. The best approximation algorithm for the minimum bisection problem in the literature achieves a guarantee of O of log n to the power 1.5. However, there is no result in the literature that rules out the possibility of a p-TAS. In the weighted minimum bisection problem, we are given an edge-weighted undirected graph, and the goal is to find a partition V into partition of V into V1 and V2 such that the sizes of V1 and V2 are almost the same, and the sum of the weights of the edges with endpoints in different sets is as small as possible. Our theorem is as follows. If the CCDM3 problem with the restriction that there are only two shifts is APX hard, then the weighted minimum bisection problem is also APX hard. Okay, so let's give the proof idea. On the left, we have an instance of the CCDM3 problem under the restriction that there are only two shifts. In this example, there are 4 applications with testing costs 1, 2, 1, and 2 respectively. All databases have uniform size, and the shift sizes are uniform and equal to 2. The corresponding weighted minimum bisection instance is given on the right. We have a vertex for each database and a weighted edge for each application. Now consider an alpha approximate solution to the weighted minimum bisection instance. In the corresponding CCDM solution, the databases corresponding to the vertices in the same cluster are assigned to the same shift. The cost of any solution to the CCDM instance is the cost of the corresponding weighted minimum bisection instance plus the total cost of the testing each application once, which is 6. We show that the approximation ratio of any solution on the left cannot be more than the same in the right. The CCDM problem is quite related to the hypergraph partitioning problem. So let me now give you the hypergraph partitioning problem. So given a hypergraph H equals V and WC, where V is the set of vertices, N is the set of edges, W is the vertex weights, and C is the edge weights. As parameter, we take the number of blocks K and the maximum block size F. The K-way hypergraph partitioning problem is to find a K-way partition pi of vertices that respects F and minimizes an objective function defined over the net. H's, basically. So there are several objective functions in the literature. The sum of the external degrees objective function is the most similar to the objective function in the CCDM problem and defined as sum over E in E, CE times lambda E, where lambda E denotes the number of blocks that contains a vertex of E. The main difference between the CCDM problem and the HGP problem variance is that in the CCDM problem, not all shifts need to be used, whereas in the K-way HGP problem, each block is necessarily non-empty. Most of the heuristic algorithms devised for the hypergraph partitioning problem use multi-level hypergraph partitioning scheme, which consists of the following 3 stages: coarsening, initial partitioning, and uncoarsening. In the coarsening stage, vertices or nets of the hypergraph are contracted to obtain series of smaller hypergraphs. In the initial partitioning stage, an initial partition is obtained by partitioning the smallest hypergraph, either by computing K-way partition directly or using recursive bisectioning until K blocks are found. In the uncoarsening stage, the initial partition uncoursed back to obtain solutions to the larger hypergraphs until a solution to the original hypergraph is obtained. At each level of the uncoarsening stage, a local search algorithm is used. We adapted 4 algorithms from 2 hypergraph partitioning frameworks, PATO and Kahipar, for the CCDM problem. PATO is a multi-level heuristic which uses recursive bisectioning to find an initial partition and use the variation of the well-known FM heuristics as the local search algorithm in the uncoarsening stage. It supports individual target block sizes and comes with 3 variations, one of which is optimized for speed, one of which is optimized for quality, where one of them is in between. The Kahipar is an n-level heuristic which only contracts two vertices at each level. At initial partitioning stage, some versions of it use recursive bisectioning and some others use direct k-way partitioning. As the local search algorithm, it uses a combination of variation of the FM heuristic and minimum flow refinement heuristic. It also provides a multi-level memetic algorithm. It also supports individual block sizes. We adapted these heuristics for the CCDM problem as follows. We first sort the blocks in the decreasing order of their sizes. Let x be the smallest integer such that the total size of the first x blocks is greater than the total vertex size. We run Kahipar multiple times with different number of blocks ranging between x and k. For each number of blocks I in the range x to k, we run path of d and path of q with the first I blocks and decrease the size of the last block by 1 and repeat this procedure until either it is infeasible or the size of the last block is 1. We also run Kahipar k the same number of times as above with the original block size. So in the experimental front, we generated 1,080 instances for each of the 8 models, which adds up to the 8,640 instances. 424 of these instances are discarded since they were infeasible or either simplex or at least one of the heuristics was unable to find a feasible solution. Now, for each algorithm, table 1 shows the average and maximum relative percentage gaps to the optimal for all the 8 models. As you can see, all heuristics perform significantly better on the instances with constant database sizes compared to the ones with arbitrary database sizes. Same can be said about application testing costs and also shift sizes, but their effects is much smaller. Now, figure 1 shows the relative percentile gap of all algorithms from the optimal solution with respect to the fraction of the instances. From figure 1, you can see that Kahipar outperforms all other algorithms and solves 65% of the instances optimally, whereas Kahipar K, path of Q and path of D solves 51%, 44%, and 34% of the instances optimal. Kahipar Kahipar K, path of Q and path of D find solutions that are 2.6%, 4.2%, 5.3%, and 5.9% within the optimal in 90% of the instances. Now, table 2 shows the percentage of instances for which each algorithm finds better solutions compared to other algorithms. For instance, Kahipar K finds better solutions compared to path of D, path of Q, and Kahipar on 44.7, 30.5, and 0.04% of the instances respectively. Path of Q finds better solutions compared to Kahipar K and Kahipar on 17.3 and 6.27% of the instances respectively. So combining path of Q and Kahipar seems to be the best choice for solving the CCDM problem. So in this talk, we revisited the CCDM problem from both theoretical and experimental perspectives. We provided a new lower bound for the running time of any exact algorithm that solves the CCDM problem. We presented a randomized 2k minus 1 over k plus epsilon approximation algorithm for the CCDM3 problem. We showed that APX hardness of the CCDM3 problem with the restriction that there are only 2 shifts implies APX hardness of the weighted minimum bisection problem. We tested the performance of the adaptations of the well-known heuristics, Pato and Kahipar, and tabulated our results. From our perspective, the following avenues of research on the theoretical front are interesting. De-randomizing the randomized 2k minus 1 over k plus epsilon approximation algorithm, designing approximation algorithms and approximate results for all the models of the CCDM problem, and developing new heuristics for the CCDM problem. Thank you for listening.